Look around you now. Look up, across distances too vast to imagine, and into worlds too small to see. The universe is singing the same song. It's a song of shape, of rhythm, of balance. Think about it, the delicate spiral of a galaxy. 100,000 light-years wide, looks uncannily like the seashell you find on the beach, or even the double helix of your own DNA. It's as if the cosmos is built from a single blueprint, whispering its secrets in a language we all know, but often forget. Geometry. The word geometry literally means to measure the earth, but our ancestors only scratched the surface. As we've peered deeper into the fabric of reality, we've discovered that geometry isn't just about our planet. It's the very structure of reality itself. Every pattern, every movement, every stable structure in existence, from the hexagonal cells of a honeycomb to the colossal storms on Saturn endures. Because of an invisible mathematical order. It's the framework that gives form to what would otherwise be chaos. For thousands of years, we've been captivated by these recurring shapes, perfect circles, elegant spirals, efficient hexagons, and mind-bending fractals. Ancient philosophers like Plato saw them as divine symbols, the eternal forms that existed in a higher realm of ideas. Today, physicists see them as the fingerprints of natural law. What Plato called divine, Einstein described as the curvature of space-time. It's fascinating, isn't it? It's two different eras, it's two different languages, but both pointing to the same profound truth. The universe's design and its laws are two sides of the same coin. So when we talk about the hidden geometry of the cosmos, we're really talking about the architecture of everything. We're asking how the Big Bang could have unfolded with such astonishing precision, creating a universe of such intricate structure. We're exploring how gravity doesn't just pull on things, but actually bends and warps the fabric of space itself, creating the cosmic dance of planets and stars. From the shimmering foam of quantum particles to the vast web-like clusters of galaxies. The same geometric patterns echo across scales that boggle the mind's 60 orders of magnitude, from the tiniest to the largest things we know. This might sound like poetry, but it's pure physics. And yet, you can't deny the beauty in it. Geometry is where science and art meet, where equations on a chalkboard transform into the glowing, filamentary structure of the cosmic web. It shows us that the universe isn't just a random collection of matter and energy floating in a void. It's a grand design, a masterpiece written in the language of symmetry, curvature, and proportion. And the most exciting part? This design might hold the key to understanding everything. By tracing how geometry emerged from the fire of creation, how it shaped the stars, sculpted the galaxies, and eventually provided the canvas for life and consciousness. We get closer to the ultimate prize, a single, unified theory that explains it all. We're on a journey to decode the universe's ultimate blueprint. Not with the dawn of humanity, not with the formation of Earth, but in the first, searing instant after the Big Bang, before matter, before atoms, before even time as we know it could be said to exist, there was something fundamental: geometry. The very structure of space-time itself. You might think of gravity as a force, something pulling you down to your chair. But according to Einstein's revolutionary theory of general relativity, that's not quite right. Gravity isn't a force pulling objects together. It's the curvature, the bending of space and time, caused by mass and energy.
Ow.
In simpler terms, the universe has a shape, and that shape dictates the path of everything within it. But before mass and gravity could take the stage, an extraordinary event occurred. A brief, almost incomprehensibly violent expansion known as cosmic inflation. This happened a mere fraction of a second after the Big Bang, we're talking about 10 to the minus 36 seconds in. In that infinitesimal moment, the universe expanded exponentially, doubling in size over and over again in a near-instantaneous flash. To put that into perspective, if the observable universe today were the size of a single grain of sand, then just before inflation, it would have been smaller than a single proton. This incredible event did more than just stretch space. It ironed it out. Imagine a crumpled sheet of paper being smoothed out under immense pressure. Inflation flattened the geometry of our cosmos to near perfection. And here's the amazing part. More than 13.8 billion years later, we can still measure that flatness with astonishing precision. we've discovered that the universe's large-scale geometry is Euclidean. That's the same geometry you learned in school, where the angles of a triangle add up to 180 degrees, and parallel lines never, ever meet. This simple, elegant geometric truth is one of our strongest pieces of evidence that inflation really happened. But inflation didn't create a perfectly smooth, featureless universe. That would have been quite boring. Instead, tiny, random quantum fluctuations, minuscule ripples, in the very fabric of space itself were stretched by this rapid expansion to truly cosmic scales. These unimaginably small variations became the seeds for all the structure we see today. Over billions of years, gravity took hold of these tiny imperfections, began amplifying them, pulling matter into the vast, intricate structures that adorn our cosmos. This is how the first filaments, clusters, and eventually galaxies were born. So, from the initial geometry of spacetime, the geometry of matter itself began to emerge. The same fundamental laws that governed the early curvature of the universe now govern the elegant shapes of spiral galaxies, the orbits of planets, and even the intricate molecular lattice that make up rocks, crystals, and indeed all life. The inflationary model actually gives us three main possibilities for our universe's overall geometry. It could have been open, curved like a saddle. It could have been closed, shaped like a sphere where you could theoretically travel in one direction and end up back where you started. Or it could have been flat, the Euclidean model we just talked about. Thanks to incredibly sensitive instruments on satellites like WMAP and Planck, which mapped the faint afterglow of the Big Bang, we now know the answer. Our universe is astonishingly flat, too, within 0.4% of perfect Euclidean geometry. The largest structure we can conceive of, spanning billions of light years, is geometrically smooth. But this incredible flatness comes with a mind-boggling puzzle. It demands an exquisite, almost unbelievable level of fine-tuning. For the universe to be this flat today, its density just 1 second after the Big Bang had to be balanced to within 1 part in 10 to the power of 60. That SA1 is followed by 60 zeros. A deviation any smaller or larger would have been catastrophic, leading either to an immediate collapse in a big crunch or a runaway expansion where no structures could ever form. This stunning precision raises profound questions. Was this perfect balance a sheer coincidence? A cosmic lucky shot? Or was it an inevitable consequence of the laws of physics? Some physicists argue that inflation naturally selects for this flat geometry, making it the most likely outcome. Others propose a more radical idea, a multiverse. They suggest that countless universes exist, like bubbles in a cosmic foam, each with its own unique curvature and physical laws. We just happen to live in one of the rare universes with a flat geometry that allows for stable structures like galaxies, stars, and ultimately us. Whatever the final explanation may be, one fact is crystal clear. Geometry defined our universe long before stars began to shine, before atoms formed, and before light could even travel freely. The very stage on which the drama of existence unfolds is itself a dynamic, stretching, curving, and evolving geometric entity. To truly understand everything that came after the majestic spiral arms of galaxies, the perfect crystalline lattice of a snowflake, the very architecture of life, we must begin here at the birth of shape itself. If you look at maps of the universe on the largest scales, you'll see something that looks like a cosmic web. Galaxies aren't scattered randomly. They are arranged along immense invisible filaments separated by vast cosmic voids. This cosmic skeleton is the direct descendant of those first quantum ripples, magnified by inflation. The same geometry that first governed the curvature of spacetime now dictates the large-scale architecture of the cosmos. In a very real sense, the entire observable universe is a geometric fossila, magnificent. Three-dimensional map of primordial waves, frozen in time and space for us to see. And so we realize that geometry is not some abstract system invented by human minds to measure land or build structures. It is a fundamental inheritance of the cosmos. It's woven into the fabric of reality. Before there was anything to see, before there was anything to measure, there was geometry. If geometry defined the birth of the universe, then it's through form that the universe expresses itself. Everywhere we look, from the grandest galaxies to the smallest snowflakes, the same symmetries emerge. patterns that seem to echo one another across scale and substance, as though the cosmos were an artist, just repeating its favorite motif. Let's begin with one of the most iconic of all, the spiral. The spiral galaxy is perhaps the most recognizable structure in the entire universe. Two-thirds of all known galaxies, including our own Milky Way, belong to this class. Their vast, swirling arms contain hundreds of billions of stars, dust lanes and nebulae, yet they all follow a surprisingly simple mathematical rule, the logarithmic spiral. Unlike the kind of spiral you might draw on a piece of paper where the arms spread out evenly, the logarithmic spiral maintains the same angle as it expands outward from the center. This self-similar geometry appears everywhere. You can see it in the terrifyingly beautiful patterns of hurricanes, in the delicate shells of nautilus creatures, and even in the whorls of seeds in a sunflower head. But why? Because nature absolutely loves efficiency. The logarithmic spiral allows material, whether it's gas in a galaxy or air in a storm, to expand while perfectly preserving its angular momentum. It's geometry born from motion, across these unbelievable scales, from millions of light years to just a few centimeters. The same mathematical constant governs their shape. The golden angle, which is about 137.5 degrees and derived from the famous golden ratio, seems to determine how leaves arrange themselves on stems, how galaxies swirl, and even how light organizes itself in diffraction patterns. It's as if the universe is humming along to a single geometric rhythm, whispered from the quantum level all the way up to the cosmic. But spirals are not the only sign of this deep order. Sometimes geometry takes on sharper forms, lines, edges, polygons, and among them stands one of the strangest and most haunting examples in our entire solar system. In 1981, the Voyager spacecraft captured something that no one expected: a perfect hexagon, nearly 30,000 kilometers across, rotating steadily around Saturn's North Pole. This isn't just a passing cloud formation. Unlike transient weather patterns, this shape has persisted for decades. The Cassini mission later confirmed that the hexagon is a stable atmospheric vortex locked to Saturn's rotation. But why a hexagon? Why not a circle, like every other storm we see in the solar system? Fluid dynamicists found an answer buried in the mathematics of wave interference. When a rotating fluid moves at certain speeds, standing waves can form. These are geometric resonances where energy patterns reinforce one another. The result can be polygons, triangles, squares, and yes, hexagons. In Saturn's case, the delicate balance of rotation, pressure, and temperature produced a six-sided resonance that may have endured for millions of years. What we see as a thing of bizarre beauty is, once again, a state of balance. Geometry emerges when nature finds equilibrium between competing force, in this case, rotation and flow. The hexagon of Saturn isn't unique in principle, but it's a powerful reminder that even turbulence, the wildest form of motion imaginable, can yield incredible structure when energy finds harmony. The same principle governs the patterns in Jupiter's storms, hexagonal ice crystals that form in clouds, and even the arrangement of carbon atoms in a sheet of graphene. Geometry, once more, is nature's language of compromise. If galaxies and storms are geometry on the grand stage, then crystals are its microcosmic perfection. At the atomic level, geometry becomes tangible. It's not a metaphor anymore. It's physical structure. Every solid object we touch owes its strength, its color, and its transparency to the specific spatial arrangement of atoms within it. Crystals form when atoms arrange themselves into repeating patterns that minimize their energy, like dancers locking into a precise formation to preserve the rhythm of the group. The result is a lattice, a geometric grid defined by mathematical symmetry. The incredible diversity of crystalline shapes, cubes, hexagonal prisms, tetrahedrons, all arises from one fundamental principle: symmetry groups. In fact, all crystals in the entire universe can be classified into just 230 possible symmetry patterns. No matter what planet, no matter what element. Geometry restricts matter's options to these discrete, specific possibilities. From the diamonds forged deep in Earth's mantle to the tiny ice grains floating in interstellar clouds, geometry dictates how atoms bond, how light refracts, even how sound travels through a solid. At the molecular scale, geometry becomes chemistry. The biological scale, chemistry becomes life. DNA, the blueprint of life itself, is a double helixon, another spiral. Snowflakes form their iconic hexagons because water molecules prefer bonding at 120-degree angles. Even viruses adopt icosahedral shells that stay shaped with 20 identical triangular faces to enclose and protect their genetic code. Across every domain of existence, form follows geometry. The great physicist Richard Feynman once said, "Nature uses only the longest threads to weave her patterns, so that each small piece of her fabric reveals the organization of the entire tapestry." Geometry is that thread. It doesn't just describe what we see, it dictates what can exist. It governs the way matter condenses, the way galaxies form their arms, and the way energy flows through space. When we recognize these patterns, we're not just projecting human math onto the universe. We are uncovering the very math the universe already uses. The hidden geometry isn't hidden because it's rare, it's hidden because it is everywhere, woven into the very fabric of reality. Geometry, it seems, is not merely a tool for describing the cosmos. It is the cosmos made visible. Here lies one of the greatest riddles in all of science, perhaps the most haunting of them all. Why does mathematics, a creation of the human mind, so precisely describe the workings of the universe? Why should the language of numbers and geometry, something we invented, not discovered, predict events billions of light years away? This question has no simple answer. It lies at the intersection of physics, philosophy, and even metaphysics, where logic meets awe. In 1960, the physicist Eugene Wigner wrote a now-famous essay on what he called the unreasonable effectiveness of mathematics. In the natural sciences, he pointed out that mathematical structures, often developed for the pure beauty of thought, turn out to describe real phenomena with uncanny precision. Think about it. Einstein's equations predicted black holes before we had any clue they existed. Maxwell's equations, born on paper, described electromagnetic waves before anyone had built a radio. And Dirac's mathematical formalism, abstract and seemingly detached from experiment, predicted the existence of antimatter years before it was ever observed. How can this be? Why should reality follow patterns that first emerge in the human mind? Some argue that math works simply because it's our own creation, tailored to fit the patterns we can measure. But that explanation falls apart when mathematics reveals truths beyond our experience, when equations describe things that only later turn out to be real. That suggests something much deeper. That mathematics is not an invention, but a discovery, a universal language, embedded in the very architecture of existence itself. One of the most radical modern ideas proposes exactly that. Physicist Max Tegmark argues that the universe is mathematics. It's not just described by it, but literally made of it. According to this view, every particle, every force, every law is simply a mathematical structure realized physically. The line between physics and math dissolves. Reality is just geometry executing itself. Tegmark's mathematical universe hypothesis implies that every consistent mathematical structure corresponds to a possible universe, perhaps realized somewhere in a vast multiverse of mathematical realities. Then is just one particular geometric solution that happens to allow consciousness to emerge. It sounds almost mystical, but the implications are, in principle, testable. If it's true, the laws of physics aren't arbitrary. They are the only laws possible within a consistent mathematical framework, long before modern science. Plato spoke of a world of forms, ideal geometries that exist beyond our material world, of which our universe is just a shadow. The perfect circle, the unbroken line, the flawless sphere, these exist nowhere in nature, yet they define the logic of everything that does. Modern physics, in its own way, agrees. No particle is truly a single point, yet quantum mechanics treats them as such. No planet's orbit is perfectly elliptical, yet celestial mechanics uses ellipses to predict their motion with millimeter precision. We live in an imperfect universe that behaves according to perfect laws. Plato might have said we live in the reflection of mathematics. A physicist today might say that the reflection is all we can see. If geometry is the universe's architecture, then symmetry is its logic. Every fundamental law of physics, from electromagnetism to quantum field theory, is derived from principles of symmetry. In the 20th century, the mathematician Emmy Noether discovered a profound connection. Every symmetry in nature corresponds to a conservation law. Symmetry in time means energy is conserved. Symmetry in space means momentum is conserved. Symmetry in rotation gives us the conservation of angular momentum. This revelation turned physics from simple description into a process of deduction. The universe doesn't just happen to be mathematically asterisk. Must asterisk be? Because its very stability depends on this geometric consistency. Even at the quantum level, particles are categorized by symmetry. Electrons, photons, quarks all are defined not by their substance, but by their mathematical transformations. In essence, particles are manifestations of geometry behaving dynamically. We are not built from stuff, we are built from symmetry. And yet the mystery only deepens. For all the order that mathematics reveals, it also exposes the limits of our own reason. Some equations break down. Some infinities cannot be tamed. Gödel's incompleteness theorems show that even in mathematics itself, there are truths that cannot be proven within their own systems. If reality is mathematical, then reality itself might contain truths that can never be known. Here lies the paradox. The more completely we describe the universe through mathematics, the more mysterious it becomes. Like light passing through a prism, our knowledge reveals its own spectrum of limits. Perhaps that is geometry's final secret, that its perfection is not ours to complete, only to glimpse. When we study geometry, we are not looking at something external to us. Our brains themselves are geometric machines. The neurons in our minds connect through networks that mirror the same self-similar patterns we see in galaxies. The same fractal organization governs the growth of trees, the branching of rivers, the architecture of our lungs, and the wiring of the human mind. It's almost as though the universe builds minds capable of recognizing its own code. In that sense, geometry is not only the structure of the cosmos, it is the structure of thought itself. And this brings us to a question as old as reason. Do we invent the patterns we see in the world, or does the world invent them in us? The answer may lie somewhere in between, in that mysterious meeting point where mind and matter, logic and light, become indistinguishable. Geometry doesn't just describe the universe, it describes the very possibility of knowing the universe. It is both map and mirror the code of creation, written in the language of reason and beauty. We often imagine geometry as a human invention, lines drawn with compasses, equations written in books, cathedrals built from blueprints. But geometry existed long before we ever named it. The arcs of rivers, the spiral of shells, the tessellation of honeycombs all were practicing mathematics eons before mathematicians were born. From deep space, our Earth rotates into view. Its oceans glimmer, its continents etched like fractals of creation. On this planet, geometry became the bridge between the cosmos and consciousness. We didn't create it, we recognized it tanned. Through that recognition, we found meaning. In the natural world, geometry isn't abstract, it's alive. Watch a flower unfurl, a shell form, or frost crystals grow on glass. You're witnessing geometry in action. The branching of trees, the veins in a leaf, the vascular networks in our lungs all follow the logic of fractals, patterns that repeat at every scale. A simple rule: split, branch, repeat. This same process distributes blood through our bodies, carves rivers through continents, and sends lightning forking through the sky. These aren't coincidences, they're consequences. Fractal geometry optimizes the flow of energy, nutrients, and information. It's nature's ultimate algorithm for survival. Even the humble sunflower encodes cosmic logic. Its seeds spiral out in two directions, forming intersecting curves that correspond to consecutive Fibonacci numbers. This elegant arrangement ensures every seed is optimally spaced, maximizing efficiency in a living system. At its core, geometry is not just decoration. It is design honed by evolution, tuned by physics, and perfected by time. Across civilizations, humans saw geometry not merely as a science, but as sacred. We built monuments that mirrored the heaven stone made to imitate the cosmos. In ancient Egypt, the pyramids of Giza were aligned with astonishing astronomical precision. Their angles encode the ratio of pi and the golden ratio, constants that also govern spirals in galaxies and the proportions of living beings. The Great Pyramid's slope of roughly 51.8 degrees reflects both geometry and cosmology, meeting point of mathematics and myth. In Greece, the Parthenon embodied a similar harmony. Its architects used ratios derived from the golden ratio to design columns, and facades that appear visually perfect to the human eye, deliberate echo of natural balance. To the Greeks, geometry wasn't just about beauty. It was truth, a visible sign of an invisible universal order. In India, mandalas express geometry as a form of meditation. These circular designs symbolize the universe's symmetry, serving as spiritual diagrams of cosmic balance. Islamic art, forbidden from depicting figures, turned geometry into a divine language. Infinite tessellations and repeating star patterns became reflections of God's infinity. From Stonehenge to the Mayan calendar, from Gothic cathedrals to Islamic mosaics, every culture discovered geometry as a bridge between Earth and eternity. When we look up at the stars, and when we look inward to create art, we are using the same principle, symmetry. It's how our minds recognize beauty and, perhaps, how the universe recognizes itself. The ancients believed the human form mirrored the cosmos, a microcosm reflecting the macrocosm. Today, science confirms this metaphor in surprising ways. Leonardo da Vinci's Vitruvian Man comes to life, overlaid with spirals and ratios. The proportions of the human body follow approximate golden ratios. From the forearm to the hand, from the navel to our total height, our very DNA coils into a double helix with 10 base pairs per turn, a geometric constant stabilized by physics. Even our brain's neural connections organize into networks that optimize geometry for both efficiency and energy conservation. Geometry shapes not only the structure of life, it shapes the function of thought. Our visual cortex responds most strongly to patterns of symmetry, proportion, and balance. It's no wonder we find beauty in spirals, hexagons, and golden rectangles. Our brains are literally wired to recognize geometry as meaningful. Beauty, then, is not an illusion. It is a biological response to geometry's harmony, the same harmony that governs galaxies and atoms. Today, our temples are not of stone, but of silicon. The logic circuits of computers, the arrangement of data networks, architecture of telescopes, all rely on geometric precision at atomic scales. The James Webb Space Telescope unfolds its 18 gold-coated hexagonal mirrors like a cosmic honeycomb. Each mirror reflects light with such accuracy that together they can detect photons from the universe's first stars. That honeycomb shape isn't just efficient, it's geometric perfection serving discovery. In our cities, skyscrapers echo crystalline lattice. In medicine, molecular modeling uses geometric symmetry to design life-saving drugs. In art, architects like Buckminster Fuller and Zaha Hadid translate mathematical forms into living spaces, reinterpreting geometry for the modern world. The same principles that guided ancient stonemasons now guide engineers, biologists, and computer scientists. The tools have changed. The code has not. Even our planet operates on geometric rules. From space, we see weather systems forming huge spirals due to the Coriolis effect. Deep within the Earth, tectonic plates are thought to form hexagonal convection cells in the mantle. And every snowflake crystallizes with a unique six-fold symmetry. All are outcomes of physical constraints translated into form. At a planetary scale, geometry helps sustain life itself. Earth's orbit lies within a narrow, habitable zone, defined by a geometric balance between gravitational attraction and solar radiation. Even the tilt of our planet's axis, 23.5 degrees, maintains the rhythm of the seasons, a cosmic angle that enables life's cycles. Our world, in every sense, is a living geometria, self-aging, self-correcting patterns suspended in the vastness of space. Humanity's greatest realization may be that recognition itself is a geometric act.
Our
Perception organizes chaos into symmetry. Our reason finds circles where there are orbits, triangles where there are forces, and grids where there is motion. We see order because we are built to, find meaning because geometry invites us to. And perhaps that is why, from prehistoric carvings to the James Webb Telescope, from mandalas to algorithms, our creations always return to the same essence, the pattern that holds the world together. The Fibonacci spiral overlays the Earth, and as we zoom outward, our planet becomes a spiral galaxy, the same pattern on a different scale. On Earth, Geometry became a mirror, one in which the universe sees itself reflected in the eyes of conscious beings. We are geometry made aware of geometry. For most of human history, geometry was the art of shapes. It was all about lines, curves, and proportions you could see or draw. But in the 20th century, something incredible happened. Geometry escaped the page and became the very architecture of reality itself. It started in the early 1900s, with a young Albert Einstein walking the streets of Bern. In 1905, he completely shattered our classical ideas of space and time. He proposed they weren't separate at all, but two parts of a single fabric, space-time. And here's the mind-bending part. Matter doesn't just sit in space. It tells space how to curve. And in return, that curved space tells matter how to move. This was geometry on a cosmic scale, a curved, invisible, yet universal geometry. By the time Einstein published his general theory of relativity in 1915, he could describe everything from a planet's orbit to the path of a light ray, not as a result of a mysterious force, but as pure geometry. Imagine a massive object like our sun, creating a deep dimple in the fabric of spacetime. The Earth isn't being pulled by the sun, simply following the curved path in that dimple, like a marble rolling around the edge of a bowl. Now, Einstein didn't invent this strange, curvy math. He discovered it had been there all along. Decades earlier, his own mathematics mentor, Bernhard Riemann, had developed what's called non-Euclidean geometry, a system where space could stretch, twist, and curve in ways that seemed impossible. Einstein took Riemann's abstract ideas and turned them into a literal map of the cosmos. Through his genius, gravity transformed from a force into a form. But a theory, no matter how beautiful, needs proof. And that proof came in May 1919. The British astronomer Arthur Eddington led an expedition to photograph a total solar eclipse. He took pictures of the stars right next to the sun's edge. Just as Einstein's equations predicted, the starlight appeared to be slightly displaced. It had been bent by the sun's powerful gravity. It was geometry in action, the curvature of spacetime made visible through starlight. The headlines were explosive: revolution in science, Newtonian ideas overthrown. For the very first time, humanity had measured the shape of space itself. But while relativity perfectly described the grand cosmic geometry of the universe, there was another realm that refused to play by the rules: the quantum world. When you zoom down to the subatomic level, geometry seems to dissolve into a haze of uncertainty. Particles act as both waves and points at the same time. Space itself appears to fluctuate like a restless sea. And yet, even in this chaos, new kinds of geometry emerge. In quantum field theory, particles are seen as vibrations and fields that ripple through spacetime, like tiny geometric notes played on the fabric of reality. Go even deeper, and you find string theory, which suggests the most fundamental components of our universe aren't particles at all, but tiny, vibrating loops of energy. Each unique vibration corresponds to a different particle. It's geometry creating matter through music. If Einstein described the universe as a four-dimensional fabric, string theory hints at 10 or even 11 dimensions. Most of them are curled up, hidden from our view, but they are still fundamentally geometric. The deeper we look, the more we find the same pattern. Geometry isn't just an option. It's the foundation of reality, written in dimensions we can't even see. Then in the late 20th century, a completely new type of geometry appeared. This one didn't describe perfect circles or smooth spheres, but the wild, irregular, and messy shapes of nature. In 1975, the mathematician Benut Mandelbrot gave it a name: fractal. Fractals are patterns that repeat themselves endlessly, no matter how far you zoom in. From the jagged edge of a coastline to the branching of a lightning bolt, fractals showed us that even chaos has a hidden structure. They are geometry's rebellion, proof that even disorder follows secret rules. Take the famous Mandelbrot set. The equation that generates it is surprisingly simple. Z becomes z squared plus c. Yet when you visualize it, you get a world of infinite detail and breathtaking beauty. It's a stunning example of complex structure emerging from simplicity, of order arising from chaos. Suddenly, the complexity we saw in nature, from river deltas to tree roots, wasn't random at all. It was governed by this recursive, self-similar geometry. The same patterns appear in completely different contexts, a hidden logic that connects physics, biology, and even art. With fractals, geometry stopped being static. It became dynamic, living, and generative. Today, physicists are once again turning to geometry as the key to a unified theory of everything. At the frontiers of theoretical physics, new ideas suggest that space and time themselves might emerge from geometric relationships, not the other way around. At Harvard, for example, a physicist named Nima Arkonahamd and his team developed something called the amplituhedron. It's a breathtaking geometric structure that dramatically simplifies the impossibly complex calculations of particle interactions. Instead of summing thousands of equations, physicists can now find answers by measuring the volume of this higher-dimensional jewel. In a way, the amplituhedron suggests that geometry itself is the universe's operating system. If this idea is right, then the universe might not be built from matter or energy at its core, but from pure geometric relationships. Space, time, and all the quantum fields could just be emergent illusions of a deeper, perfect geometry. Einstein once said, "Pure mathematics is, in its way, the poetry of logical ideas." Today, poetry continues to be written, not in words, but in dimensions. When we look at the largest scales, we see galaxies clustering along massive filaments, forming a cosmic web. It's a vast fractal-like lattice stretching across billions of light-years. Between these filaments lie enormous voids, empty regions shaped by the geometry of gravity. The very structure of our universe mirrors the branching of neurons in our brain and the forks of a river, the same geometric logic repeating at unimaginable scales. From the microcosm of atoms to the macrocosm of galaxies, everything is geometry arranged by energy and time. Every generation of scientists, from Euclid to Einstein to the physicists of today, has peeled back another layer of reality's geometric skin. And with each new revelation, the universe seems both simpler and stranger at the same time. The more we measure, the more we realize geometry is not just a tool we use to understand the universe. It is the universe, the silent, elegant architecture hidden beneath all phenomena. From the bending of starlight to the folding of our DNA, from the shape of clouds to the spin of an electron, geometry connects all things. It is the mind of nature made visible through pattern. We've spent centuries trying to understand the universe by breaking it apart into matter, energy, forces, and particles. But what if we've been looking at it all wrong? What if the secret isn't in the pieces, but in the pattern that connects them all? In the end, it's possible that everything from the smallest quark to the largest galaxy boils down to one thing: geometry. Not the kind you learned in school with rulers and compasses, but a deeper, more profound geometry of relationships, symmetries, and transformations. The invisible mathematics the universe uses to think, from Newton's universal gravity to Maxwell's elegant equations for electromagnetism, all the way to Einstein's relativity and the bizarre world of quantum mechanics. Every great leap forward in physics has uncovered a deeper geometric order. Each breakthrough took a world that seemed chaotic and showed that what appeared to be different forces or particles were actually just different facets of a single, elegant structure. Einstein spent the last decades of his life chasing a unified field, theory, a single master equation that could explain all of reality. He never found it, but that dream is more alive today than ever. Modern physicists are continuing that quest, armed with mathematical tools that Einstein could only have dreamed of. And once again, at the absolute frontier of science, geometry is leading the way. So how does this work? Theories like quantum gravity, string theory, and loop quantum gravity, while different, all share a common belief: reality is geometric at its very core. In loop quantum gravity, for example, space isn't a smooth, continuous sheet. Instead, it's woven from tiny, discrete loops, indivisible quanta of area and volume that form a network called a spin foam. Space-time itself becomes a quantized geometry, built from relationships at the smallest possible scale. String theory takes this a step further, imagining these fundamental units as tiny vibrating strings and membranes existing in extra dimensions. Each unique vibration corresponds to a different particle we see in our universe. Every interaction is a dance of pure geometry. And then there's the mind-bending concept of the amplituhedron. It's a newly discovered geometric object that simplifies the incredibly complex calculations of particle interactions. It suggests that the properties of space and time might not be fundamental at all, but instead emerge from a more basic, timeless, purely geometric reality. If these ideas are on the right track, they paint a picture of the universe as a self-organizing geometric system, a grand structure that creates itself. Through the fundamental rules of symmetry. Symmetry is a word we hear all the time, but in physics, it's a concept of immense power. Physicists have long known that symmetry is directly connected to nature's laws of conservation. For every type of symmetry found in the universe, there's a corresponding quantity that is always conserved. For example, the laws of physics working the same everywhere in space corresponds to the conservation of momentum. The laws working the same at all times corresponds to the conservation of energy. In fact, the entire standard model of particle physics, our best description of all known particles and forces, can be described using the language of geometric symmetries called Lie groups. These are abstract shapes that exist in higher dimensional spaces. From this perspective, what we call forces are simply the geometric consequences of these symmetries interacting with each other. It's a profound shift in thinking. Physics might not be about asterisk things asterisk at all, but about the asterisk relationships between things asterisk, the geometry of interaction that defines reality itself. But perhaps the most mysterious and intimate geometry of all is the one found inside us. Our brains also operate on geometric principles. Neural networks are wired to minimize distance and maximize efficiency, constantly forming and reforming patterns to process information and detect symmetries in the world around us. Some cutting-edge theories even propose that consciousness itself might emerge from a specific kind of geometric organization, patterns of information and energy flow, forming complex self-referential loops within the brain. Theories like integrated information theory suggest that your subjective experience, the feeling of being you, right now, could be a direct property of the asterisk shape asterisk of the information being processed in your mind. In this incredible view, awareness is a special kind of geometry that the universe uses to observe itself. We are, in a very real sense, geometry observing geometry, the universe made aware of its own magnificent design. In the coming decades, this geometric revolution won't just reshape our understanding of the cosmos, it will transform our technology. Quantum computers already operate by manipulating information as geometric vectors in a high-dimensional space. Artificial intelligence learns by mapping vast data sets into multidimensional landscapes, finding patterns and structures. It's geometric learning at digital speed. Physicists are now talking about entering a new geometric phase of science, a phase where complex equations give way to powerful visualizations, and where the next great discoveries might come, not from crunching numbers, but from simply seeing the underlying structure. Imagine telescopes that can map the actual shape of space-time around a black hole, or AI models that can perceive hidden symmetries in the laws of nature that are invisible to the human mind. The next revolution in science may not come from a bigger particle collider, but from the next great leap in our understanding of geometry. This all leads to the ultimate question. If the entire universe is fundamentally geometric, what or who set the rules of that geometry? Why does existence bother to follow mathematical laws at all? Why should the very fabric of reality care about concepts we find beautiful like symmetry, order, and elegance? These are questions that push beyond physics and touch on philosophy at the boundary where science meets mystery. Perhaps geometry doesn't just describe the universe. Perhaps it is the universe, the fundamental framework through which formless energy becomes structured matter. Matter organizes into life, and life awakens into consciousness. If that's true, then geometry isn't just the foundation of reality. It is the process of reality becoming aware of itself. From the tiniest particle to the largest supercluster of galaxies. From the curve of spacetime to the architecture of our own thoughts, geometry is the silent, unifying order that connects it all. It's the hidden structure beneath the chaos, the bridge between the physical and the metaphysical, the code that allows the cosmos to know itself. Perhaps one day, when the final theory of everything is written down, it won't be a long string of symbols and numbers. It will just be a shape. Thanks so much for exploring these incredible ideas with me. If you enjoyed this journey to the edge of science, don't forget to like this video and subscribe for more deep dives into the biggest questions in the universe. See you in the next one.